So let me show you a little bit of how we might address the question of the density of primes using the more modern tools that are at our disposal. So if we go to Maple, then I'm going to show you something that I've pre-prepared, and also I will put this, of course, on the Epsilon page so that you can play with it yourself. I'm going to start loading some packages into Maple. This is one of the reasons why we're using Maple, is that Maple comes with a lot of built-in stuff. So for instance, there is defined somewhere here a function pi that simply counts the number of primes less than a certain number. So we don't have to like Gauss look in tables or things like that. We can very easily have these numbers computed using pi. So for instance, if I wanted to see how many primes are there less than 500,000, this is something that I can get directly out of Maple. So what I'm going to do is to get a feeling for the density of primes, I'm going to select a number, the number 500, and then I'm going to look at an interval of with 500 around the numbers 1000, 1001, and so on. Let me start this computation because it takes a little time, and then divide by 500. So it's a density of primes in a 500 interval around n, where n varies from 1000 to 10,000, like this. Right. So you can see, of course, there's some very systematic changes. So these will actually not. I mean, this is a function that is clearly much more complicated than something straightforward like 1 over the logarithm, which is what Gauss conjectured that we would see here. But in fact, if you know Gauss's conjecture, then it somehow seems reasonable. Now I've plotted 1 over logarithm of n with these observations, and it does look reasonable that what we're seeing here is somewhat related, so that these are fluctuations around a general decay which looks like 1 over the logarithm. So this would seem to corroborate Gauss's conjecture, and indeed we know it's true because of the prime number theorem. You can see that I'm using various kinds of tools to make this into a nice drawing, a drawing where we can sort of see the key features, and this is something we're going to come back to when we discuss visualization in one of the coming weeks. There's various ways to help Maple make a nice plot, which is easier to process for the human eye. But also something that we're going to come back to is that we're not completely on our own when we try to analyze observations like this. So we don't have to be as clever as Gauss, fortunately. So let me give you an idea of the kind of basic tools that are available to us. So for instance, suppose that we somehow got the idea that instead of looking directly at the density of primes, we would look at the reciprocal of the density of primes, right? So I'm plotting that now. So instead of taking these numbers directly, I will just take the reciprocal. So I have observations that look like go down to roughly a little under a tenth, and when I take the reciprocal, I will get various values around 10. I've also increased the size, so I'm now going all the way out to 50,000 rather than just 10,000. And you can see perhaps it's a little bit easier to process this visually, so you could perhaps, if you looked at this, you could get the idea that if you sort of cancel out all the fluctuations, this looks a little bit like the graph of the logarithm. But my point is that here we can actually start to use basic tools that arise in the natural sciences. When you have observations, we try to understand observations. Very often we're trying to see if we can find a linear relation between what's on the x component of some observations and what's on the y component of the observation. And one of the standard tricks that I'm sure you're familiar with, maybe more from doing physics in high school than from doing mathematics perhaps, is that we can change the axis so that one of the axes is logarithmic rather than straightforward, so that corresponds to the semi-logarithmic plot paper that you may have been subjected to at some point. It's very easy to do this directly in Maple. We just change the properties of the axis to be log mode. And so you can see what I've done here is that I've changed the x-axis to be logarithmic. Usually you would change the y-axis if you're trying to understand something which is exponential, but here I have a growth which is essentially logarithmic, so it's the x-axis that I have to change into a logarithmic scale, and then I will get something that actually now begins to look like it's linear. Right, so you see, my point is here that we have tools in order to process the data that will help us visually simplify what we're seeing, so that perhaps we can recognize this as essentially a line with something with some noise on top of it, of course. And furthermore, we have tools, and we're going to discuss this systematically, to find, for instance, the best straight line that goes through some observations. This is a standard sort of fitting least square type of problem, and so we will get back to how this works, but I'm just essentially asking Maple to compute the real line that is the best approximation to these observations here. As you can see, it takes a little time, but here's the answer. So Maple claims that the best approximation, linear approximation to these observations. So, I mean, essentially, I took the observations and I explicitly made the x-axis logarithmic by taking the logarithm of n up here, and then I'm taking the original y observations, and then I'm finding by the least squares method, I'm finding the best approximation, and this is what it looks like. And so you can see that you can very easily get the idea that perhaps this number is 1, in the sense that what we have here really should have been 1, but because of the little fluctuations and so on, we're not getting exactly 1. Right? So I'm making an interpretation to say that, well, this number here, I'm not going to take that on face value. I'm going to think that perhaps this is 1. And if we believe that it is 1 and we sort of transfer back, then we would exactly get the theory or conjecture, like Gauss did, that the density of primes is 1 over the logarithm of the center of the interval that we're looking at. Right? And so putting everything together in one plot, let me see if you will find this convincing. So these are the observations now in red, and this is the line, and you can see that it seems to fit fairly well. And my point here is that we have tools to help us process data from an experiment, and this is something we of course are going to discuss systematically later on in the course.